Okay, so in this video we're going to construct the Mayer-Vietoris sequence. So let's recall the basic setup. Let X be a topological space. And we're going to suppose it's a union of two subspaces, U and V. U and V are both open. Okay, and so we're going to prove the theorem about the homology of X, which of course is based on the chains of X. And so it turns out to make it work properly, we need to consider only small chains. So we need to explain what that means. So I'm going to say that a map U from delta n to X is small. Either the image is contained in U or the image is contained in V. So more generally, let's consider a chain like this. So it's a linear combination. As usual, the mi are integers and the ui are maps from delta n to x. So I'm going to say u is small if each of the corresponding terms, each of these maps ui is a small map. So basically what we're saying is that the small singular symphyses of X is just the union of SNU and SNV. And then the small chains, the chains like this, well, you can think of those as just being the subgroup CNU plus CNV, right? If all of these are small, some of the terms are in CNU, some of the terms are in CNV. Add them up, you're in CNU plus CNV. Okay, so C star X is a chain complex, C star U is certainly a subcomplex. So if you've got some map going into U, then all the faces will also go into U. You've got a map going into V, then all the faces will go into V. So the C star U is closed under the boundary operator, under the algebraic differential, and so C star V, and so therefore so is the sum. This is a subchain complex. I want to claim though that the homology of this complex of small chains is the same as the homology of the full complex C star X. Okay, yeah, so C star small. Let's just write this definition again. So so we've got. So I'm going to claim that if I start with an arbitrary simplex here in C star X, and then let's say CNX, then for large K, the K-fold subdivision of U will be small. Okay, so the proof will. Okay, so so of course U could be a linear combination of maps like this, but for the moment we're just going to assume that it's just a single map from delta n into x. Okay, so then let's put U prime is the preimage of U, and V prime is the preimage of V. So that means that U prime and V prime together, they give an open cover of the compact metric space delta n. Okay, okay, because I mean every point x is equal to U union V, so every point in delta n either gets sent into U or gets sent into V. So these sets they cover delta n, and of course U is continuous, preimage under a continuous map, and open sets open. Okay. Okay, so a long time ago we proved this fact that any open cover of compact metric space has a Lebesgue number. Okay, so there's some positive number epsilon greater than 0. So that means that every ball of radius epsilon in delta n is either contained in U prime or in V prime, or maybe both, but yeah, at least one or the other. Okay, so so yeah, we've got let's consider we need to think about diameters of simplices. So we look at the identity simplex on delta n. Okay, so that's just a simplex. There's the identity map from delta n to itself. So the diameter of this is the maximum possible distance between two vertices of delta n, and those are like unit vectors in R to the n plus 1. The distance between two of those is root 2. So if we do a k-fold subdivision of iota n, it's the diameter of that. That's going to be less than or equal to, we had this lemma about the subdivisions. We get n over n plus 1 to the power k times the original diameter, which is root 2. Every time we subdivide, we get a factor of n over n plus 1. And of course, this is going to converge to 0. So that means that for k, when k is large, every simplex in st to the k iota n has diameter less than epsilon. Therefore, is contained in U prime or V prime. And that means that every simplex we apply U hash to this. That's the same as just getting the k-fold subdivision of U. Okay, so k-fold subdivision of U is what we get by taking the k-fold subdivision of iota n and pushing it forward by U. And if you've got a simplex that's contained in U prime, when you push it forward by U, it'll end in U. And if you've got a simplex that's contained in V prime, when you push it forward by little u, it'll be contained in little v. So that's okay. So this if we start with just a single map u from delta n to x, and you subdivide it enough times, then it will become small. Okay, so the general case where you've got an element in CNX, it's a linear combination of maps like this, and you subdivide each one enough times, then it will become small. So if you subdivide the whole thing enough times, then each of the individual terms will become small as well. Okay, so this proves what we said, that if you subdivide a thing enough times, then it becomes small. Okay, so now recall we have okay, we've got the subdivision operator which sends CNX to CNX. It kind of also sends CNU to U, CNU and CNV to CNV, and therefore it sends Cn small x is the sum of these two things, so this gets sent just Cn small of x. And then we also had this chain homotopy from Cnx to Cn plus 1x, d sigma plus sigma d is the identity minus subdivision. And but from the way it's constructed, it's easy to see that this sends CNU to Cn plus 1u, CNV to Cn plus 1v, and and therefore it sends the small to Cn plus 1 small. Okay. And so now we can form the quotient. Okay, I'm going to define define Qn to be the quotient, Cnx modulo the small stuff. Okay, and we find that so because it's sending the subdivision is sending Cn to Cn and Cn small, it induces a map Qn to Qn. And similarly over here, we get a sigma, and we're still going to call this map SD. And we're going to call this map here. You also get an induced map here from Qn to Qn plus 1. Okay, so this Q star, notice also this, again, you've got the differential from Cn to Cn minus 1, that preserves CNU, CNV, and Cn small, so this, you've also got an induced chain, induced differential on Qn. This is a quotient chain complex, and so we've still got we've got a well-defined D on Qn, and you've still got D sigma plus sigma D as the identity minus subdivision. Because that's true on Cnx, it's going to be also true on this quotient complex. Okay. And because of that, if you've got chain homotopic maps, then they induce induce the same thing on the homology. That's a key fact about chain homotopies. So we're seeing that the subdivision is the identity on the homology of Q. Okay, so now I want to claim this complex Q that we defined, the full chain complex modulo the small chains, that the homology of Q is just equal to 0. So with that, well, so let's suppose we've got some element little q of in dimension n here. So q, that means that it's the it's represented by some some element in Qn. So that means that this element Q tilde, this has got to be represented by some U in CNX. It's remember Qn was defined to be the full chain complex modulo the small chain, so it's this Q tilde is some coset like this. So we showed that for large K, the K-fold subdivision of U is small. And that means that if we do the induced subdivision operator on the quotient, the K-fold subdivision of Q tilde is just going to be 0. It'll be represented. It'll be like SDKU plus the small thing, but SDKU is already small, so that's the 0 coset. And that means if for the induced subdivision operation on homology, the K-fold subdivision of Q is 0. But we know that the subdivision is as we mentioned on the previous slide, the subdivision is chain homological identity, so it acts as the identity in homology. So the subdivision of Q is 0. That just means that the K-fold subdivision of U is 0. That just means that Q is 0. Okay, so every element in the homology is 0. The homology groups of Q are all just 0. So as a corollary of that, we just look at the inclusion from the small complex to the full complex. Well, it uses an isomorphism. From the homology of the small complex to the homology of the full chain complex of X. And of course, this is just by definition what we mean by the homology of X. And the proof so we've got an short exact sequence of chain complexes and chain maps. We've just got this inclusion here, and then just the obvious kind of quotient map onto the Q star, which was, remember, that was just defined to be this quotient. So now we use the snake lemma. The snake lemma gives us an exact sequence, hn plus 1q, going by delta at hn of the small complex. To hn of x, and then to hn of q. Okay. But we've shown that this q has homology groups are 0. And remember, so the kernel of ink star is the image of this delta, which has to be 0, and the image of ink star is the kernel of the map from hnx to 0, which is all of hnx. So if the image of delta has to be the kernel of ink star, so kernel of ink star is 0, ink star is injective and also surjective. So this is an isomorphism. Okay, so now we're nearly done. Okay. So we've got inclusions. Remember, you've got U intersect V. We got inclusions I and J into U and V, and then inclusions of both of those into U union V, which was X. So K composed with I is the same as L composed with J. And so you've got C star U intersect V. It goes by I hash to C star U. And J hash to C star V. And now here I could write C star X, but yeah, so well, let's do this a minute. So you've got your K hash here and your L hash here. Okay, so these are just the inclusions of C star U and C star V and C star X. So they're actually ending in the small complex. Okay, so here you've got these maps both going to the small subcomplex of X. Okay, with so now we can assemble these into a sequence like this. So we've got these maps like here. So this is going, so U goes to I hash U, comma minus J hash V. So minus J hash U, and this is the thing that goes VW goes to K hash V plus L hash W. And yeah, the fact that this commutes means that if you do both this map followed by this map, then you get 0. Okay. Yeah, so I want to claim this is a short exact sequence. Okay, so the point about restricting to the small complex is the small complex is basically by definition the image of this right-hand map. Okay. And now it's pretty easy to see because I and J are injective. So is minus I hash J hash. Okay. Okay. And then yeah. So we know this map's injective, that one's surjective. We know that the composite is 0. Composite is 0, so that means that the image of the first map contained in the kernel of the second one. And I want to claim also that the image of this first map is the same as the kernel of the second one. Okay, so yeah, so to prove exactness in the middle, we need a few more definitions. So we're going to just put, so let me put Sn prime U So Sn prime U is the maps into a U which don't land in U intersect V. And then I'm going to put Cn prime U is the free abelian group generated by Sn prime U. Then you define Sn prime V and Cn prime V in a similar sort of way. Okay. Then it's pretty easy to see that your CNU is just CNU intersect V, direct sum Cn prime U. Your CNV is CNU intersect V, direct sum with Cn prime V. And then the small complex, small group Cn small x. Okay, here you've got stuff that either lands in U or it lands in V, so it's the sum of these two groups here. So this is CNU intersect V plus Cn prime U plus Cn prime V. Okay. So our sequence is now looking like CNU intersect V, going to then in the middle here you've got your CN U intersect V plus Cn prime U plus Cn U intersect V plus Cn prime V. Yeah, and then the last term here, there's the small thing. And one of the maps, so this is kind of like x going to x0 minus x0. And then this map is like x, u, x prime, v goes here to x plus x prime, uv. And from this description, it's pretty clear that this is short exact. And so it's very easy to understand. Well, firstly, it's completely clear that this map's injective from this description, and then this map is also surjective, because xu0v goes to xuv, so that's surjective, and then the kernel of this is equal to the image of that by straightforward calculation. Okay, so this is short exact. So we can apply the snake lemma to this, which is going to give us a exact sequence like this from Hn plus 1 of the small complex for x, and then via delta going to Hn of this complex here, which is just Hn of the space U intersect V, then HNU plus HNV, and Hn of the small complex, and down to Hn minus 1 of U intersect V by delta again. Okay, but then the whole point of the first section of this video was to show that this homology is just the same thing as the ordinary homology of x. This one is just the ordinary Hn of x. So what we've got here is now the Mayer-Vietoris sequence. Okay, so this completes the construction of the Mayer-Vietoris sequence. We had to produce this short exact sequence of chain complexes here, and then there was this whole point about subdivision to check that the small complex had the same homology as the full complex, and then we had this whole story about the snake lemma, to show that this short exact sequence of chain complexes like this will give us a long exact sequence of homology groups.